Welcome to The Explainer. Today, we're going to decode the elegant principles behind pretty much every machine that moves. You know, from the engine in your car to the clock on the wall, there's a hidden language of motion at work. And to help us understand it, we're going to use these fantastic university engineering notes as our guide.
Okay, so let's kick things off with a question that gets right to the heart of mechanical engineering. It really does seem kind of like magic, doesn't it? You have this one simple input, just rotation, and somehow you get 1,000 different complex outputs. How is that even possible?
Well, the answer isn't just about brute force or raw power. It's about intelligence, designed right into the geometry of the machine itself. Take a look at this diagram on screen. It's a perfect example. It looks like just a collection of simple links and pivots, right? But when they work together, they take that simple rotation and turn it into a very specific and very clever movement. All right, so let's really dive into this. To get a handle on the subject, we've got to clear up a really important distinction that engineers make. What's the actual difference between a machine and a mechanism? They sound similar, but they're not the same.
Okay, so check this out. What's so cool about this is how it separates the what from the how. A machine, like a lathe or a drill, is the whole shebang. It takes in energy and actually does useful work. But the mechanism, that's the genius inside. It's the skeleton outline, the clever blueprint for the motion itself. So think of it this way. Every machine has a mechanism at its core, but a mechanism by itself, like the linkage in an old typewriter, isn't necessarily a complete machine.
So, for the rest of this explainer, we're really going to focus on these brilliant blueprints for movement. Just think of them as the fundamental vocabulary in this language of motion. By combining them in different ways, engineers can create pretty much any movement you can think of.
All right, now that we've got that down, let's look at a few really ingenious mechanisms from the engineer's toolkit. These are like the classic go-to solutions for some very common problems in machine design. First up, we've got the quick return mechanism. And this thing is just so incredibly efficient. Imagine you're doing something like cutting metal, right? You only need power in one direction. You want that forward cutting stroke to be slow and powerful, but then you want the return trip to be as fast as possible to save time. This mechanism nails it, and it does it all with just one simple constant speed motor. It's brilliant.
And then there's this. This solves a classic engineering puzzle. I mean, how do you get something to move in a perfectly straight line using only parts that pivot and rotate? Seriously, it's way harder than it sounds. This is Robert's mechanism, and it's this beautiful 4-bar linkage that guides a point along a nearly perfect straight line. This was a huge deal before we had all the modern high-tech linear guides.
You know, that quick return idea we just mentioned? It's just too clever not to look at more closely. So, how in the world does it actually work?
Okay, so here's the entire system laid out. You've got your motor spinning this small driving link. That's part 3. See how it has a little pin on it? That pin slides back and forth inside the slot on that big lever, part 1. And it's that rocking motion of the big lever that pushes the tool, which is part 6, back and forth.
And the secret sauce here? It's all just simple geometry. You can see it right here in the diagram. Look at how that small spinning crank is offset. It's not centered with the big lever's pivot point. So as it goes around, it has to cover this really big angle, alpha, to do the forward stroke. But for the return, it only has to cover that much smaller angle, beta.
So what does that mean? Well, since the motor's speed doesn't change, a bigger angle just means it takes more time. So you get this long, slow, powerful cut on the way out, and then a super fast return trip to get back into position. Simple, right? It's just genius, and it's all done mechanically. No computers, no fancy electronics needed.
And believe me, this isn't just some drawing in a textbook. This exact setup is the beating heart of real industrial machines, things like shapers and slotters and power saws, and it makes them way more efficient. But you know, getting the motion right is really only half the battle. Because once you start making machines bigger and faster, you suddenly have to deal with some seriously powerful forces.
Okay, just picture this. You've got heavy metal parts spinning thousands of times a minute. Even if one part is off balance by the weight of a tiny coin, it can create these insane shaking forces. Dynamic balancing is the art of figuring out exactly where to put counterweights to cancel all that out and make it perfectly smooth. I mean, without this, your car engine would literally vibrate itself to pieces. So what about when the load on an engine changes all of a sudden, like when a big generator kicks in? That's where a governor comes in. It's basically a mechanical brain, a feedback system. As the engine spins, these weights fly out. The faster it goes, the farther they fly out, and that motion closes the throttle. If it slows down, they fall back in, opening the throttle up. It's a completely automatic speed controller, and it's all just physics. So cool. And finally, we've got to talk about vibration. The best way to think about it is like pushing a kid on a swing. If you push at just the right moment at its natural frequency, they go higher and higher with almost no effort. Well, the same thing happens in a machine. If the vibration from the engine happens to match the natural frequency of some other part, that part can start shaking so violently it just breaks. Controlling that is a massive, massive challenge for engineers.
So, look how far we've come. We started with a pretty simple question about a spinning motor, and now we're talking about the fundamental blueprints of all motion and these huge, dynamic challenges that engineers have to wrestle with every single day.
And the big takeaway, really, is that this stuff is absolutely everywhere. Once you get the idea of a mechanism, you start seeing them in places you never would have expected. Your car's engine, sure, but also your windshield wipers, or even just a simple pair of scissors. It's like putting on a new pair of glasses to see the world.
And that kind of brings us to a final question for you. Just take a second, look around you right now. Can you spot any of these hidden mechanisms? The little linkages, the sliders, the gears? Because once you start looking for this hidden language of motion, I promise you'll start seeing it and appreciating it absolutely everywhere.